So now we want to learn about some connection between coloring and polynomial. So our goal is to prove the following theorem by Alon and Tals. So again, we have some orientation or some diagram, say diagram T. And if we know that for each vertex P, we compute its out degree. And then for each vertex, we assign this F value, which is out degree plus 1. Then we want to find some sufficient condition for the graph, the underlying graph become F choosable. So again, we have this undirected graph, and then we give some, orientation to obtain this diagram T. And in this orientation, we have this out degree, and then from that, we want to find some sufficient condition where that we can ensure that the underlying graph is F choosable. So for that, we need to define this concept. And we say a diagram T is a circulation if every vertex has the same out degree and same in degree at the vertex. So for example, if we have a graph which looks this way, say, then this is a circulation because every vertex has a in degree out degree 1, 1, 1, 1 here, and then here in degree and out degree are 2. And we say the parity of a circulation is the parity of the number of edges in it. So here we have 9 edges. So this is odd circulation. And we write the diff of this D to denote the difference between the number of even circulation and number of odd circulations, which is totally contained in D. So for example, if we consider an empty diagram with no edges, then that's an even circulation. So we consider, that as an even circulation. So we count it here. So, and also we consider this circulation or this diagram as a set of edges. So for example, if we have in D, if we consider these 3 edges, then that's one odd circulation, which is contained in D. But if we take this one vertex and these 3 vertex and these edges, then that's again an odd circulation, but we consider those two same. Because, as a set of edges, they are the same circulation. So we consider this as a set of edges. So now what this says is that if we have a diagram whose number of even circulations and number of odd circulations are different, then this D is F choosable, where F is 1 more than the out degree of the vertices. So before proving this, let's see some application of this. So one application is that, we define the maximum average degree of G with the maximum of among all subgraph H of G, we add all the degrees of the E, which yields the twice of the number of edges, and H, and we divide it by H. So this is average degree of H, and we take the maximum out of it. So instead of average degree, we take this maximum average degree, because in many cases, for example, if we have a graph G, and then this has average degree 3, so this measures how dense it is. But in many problems, in many problems like the graph coloring or other problems, if we add some more vertices, for example, in coloring problem, if we add some more isolated vertices, then the chromatic number doesn't go down. But if we add these vertices, the maximum average degree goes down. Now this has 6 edges and then 10 vertices. So maximum, the average degree go down to 13, half. No, 12. So less than 1. So if we want to, state some theorem, say we want to say that if graph is dense or sparse, then its chromatic number is something. Then when we want to measure this dense or sparseness of the graph, average degree is not a good, unit, not a good parameter, because adding this, dummy structure can lower the average degree while it doesn't lower any chromatic number. Similarly, you can have a large graph G, and here we have very dense part, and then here we have very sparse part. Then we don't really care about the density of this part. We only care, more important thing is that what's the maximum average density, average degree in here. So that motivates us to define this maximum average degree. And we know that by the problem 4-1 in homework 3. So there it's written as ensuring the in degree, but we can easily flip the out degree and in degree. So we can actually show that every graph has an orientation so that each vertex has at most half of its maximum degree, taking shilling many out neighbors. Okay, then from this we can actually prove this, that every bipartite graph G is half maximum average degree, taking shilling plus 1 choosable. Why is it? So first, we can check that for bipartite graph, if you orient the edges in arbitrary way, then its difference of D is always non-zero. Why? So, what are the circulation? The circulation is actually you can actually see that this is disjoint union of Euler subgraph. So Euler subgraph are the ones that satisfy this and connect it, and which is also, can be expressed as the Euler circuit, Euler tour. So you visit the edges and then you come back. While you're visiting each edge once. Anyway, that's nothing but a disjoint union of Euler subgraph. And for bipartite graph, if you consider a circulation, in bipartite graph, every cycle has a length even. And this Euler subgraph is actually edge disjoint unions of cycles. It's one of the facts that we learn in the undergraduate graph theory. So that's the disjoint union of cycles, and in bipartite graph, every cycles are having even length. So every circulation is even. There is no odd circulation. And there are at least one even circulation, because empty set of edges is a trivial even circulation. So this condition satisfied. So by Alon-Tarski theorem, we just take this specific orientation. Then in here, this is upper bound on the out degree of the orientation. And then this is bipartite graph. So for this specific orientation, we also have this. So Alon-Tarski theorem implies that this is true. In particular, this shows that every planar bipartite graph is choosable. Because by using Euler's formula, we know that if you have a bipartite planar graph, then it's 4 degenerate. So we can show that its maximum average degree is at most 4. So half of that is 2, so this number is 3. So you apply Alon-Tarski theorem, then you can conclude that every planar bipartite graphs are 3 choosable. Another application is cycle plus triangle theorem, proved by Fleischner and Stibitz in 92. This was conjectured by Erich on 87 or something. So what it says is that if you have a 4 regular graph, which is union of cycle of length 3n, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then you take you add some triangles in an arbitrary way. So you add m triangles in each disjoint way. Then you get this 4 regular graph. And Erich conjectured that this is 3-colorable in however way you add the triangles. And they actually show that this is 3 choosable by using Alon-Tarski theorem. And so that shows several applications of this Alon-Tarski theorem. And now we want to see why this, orientation and coloring, the chromatic number, are related. So in order to prove this Alon-Tarski theorem, let's just first see what's the intuition, why this orientation has something to do with the chromatic number. For that, we need to first define this graph polynomial. given a graph G with vertices V1 to say Vn, and we consider the graph polynomial, say P sub G of G is defined by the following. So there are n variables, x1 to xn, is you just say, let's write it more bigger way. You consider all ij where j is bigger than I, where vi, vj is an h in G, and you multiply xi minus xj. Then this polynomial carries the full information of the graph. So actually, in early days, I mean, one of the motivation to study graph is to study this polynomial. That's some of the reasons why we define some terminology in that way. For example, we say degree of a vertex. That comes from this polynomial. I mean, it has, so this xi is corresponding to this vertex vi. Then degree of xi in this polynomial is degree of v. And also some term like factor. Also that comes from this polynomial. And lots of, I mean, terminology actually stems from this definition. So here, I mean, what's the relationship between this and chromatic number? Let's just assume, for now, let's just assume that whatever graph we consider, we always have this ordering of the vertices, V1 to Vn. Then, we know that let's say we are working on a real number, then this polynomial becomes 0 if and only if we assign, say, xi to vi creates no, let's just imagine in this way. Let's say that we are assigning colors, and then those colors are numbers. And if we assign some color, say 1 to vi, then we imagine that as assigning color 1 to xi. Then, in here, this polynomial, let's write this as a number, say, okay, t1 to tn. If we assign ti to vi, write it this way. Assigning this value ti to each vi creates a monochromatic edge. Then we get this polynomial become 0. And if this polynomial is 0, that means this assignment creates a monochromatic edge. So this polynomial is related to the chromatic number of G, or coloring of G. More correctly, I mean, we are interested in when does this polynomial vanish and when does it not vanish. So that's the relationship between this polynomial and chromatic number. But also this polynomial has relationship with orientation of the graph. Because if we have this, then this is multiplication of many terms, x1 minus x2, x1 minus x3, and x3 minus x5, and multiplication of this. if you split everything, then this gives you many terms. And each of the terms can be formed by multiplying these things. So let's say here we choose this, here we choose this, here we choose this, then we get x1 to the 1, x3 to the square, and so on. And it could be have a plus 1 or minus 1. So each term looks this way. But in graph, this is V1 and V2, and V1, V3, V3, V5. Choosing this is as if we are choosing the orientation. There are two ways. So we can either choose, 3 to 5 way or 5 to 3 way. That's same as you either choose 3 or you either choose 5. So each term here, so if you, compute this, you expand it, then each monomial you get has a one-to-one relationship between this orientation of the given graph. But also, when does this polynomial vanish has something to do with what monomials you have. So that's vaguely why we have the connection between the chromatic number or the coloring and this orientation of the graph. So in next video, let's start the proof of this alone-Tarski theorem and then see, what's the connection between this, orientation and coloring or choosability in this case.